Okay. So first, I also would like to thank the organizers for inviting me to this interesting workshop. In this talk, I want to show some more exotic applications of these trapped ion systems. And I will focus on two examples. For the first example, we want to see that with trapped ions, we can realize the so-called space-time crystal. The time crystal is actually a recently proposed, pretty controversial concept by Frank Wilczek. And we will see that the trapped ions at least can realize this kind of exotic state of matter at some macroscopic scale. And for the second part of the talk, I want to change the gear to a different application of the trapped ion system to study some dynamic phase transitions. So we are familiar with normal phase transitions for the ground state or for the thermal equilibrium state, but this is some transitions associated with the system dynamics. And in particular, we want to show that the trapped ions can be used to realize some pretty unusual phenomena called pre-thermalization. It's a step towards thermalization. It's kind of like a macroscopic state which will be stabilized for long times. So normally we call it a pre-thermalization. So let's first come to the concept of time crystal. What's a time crystal? And these are a few references in this direction. And first, let me briefly explain the basic concept that we mentioned before. This is proposed by Frank Wilczek about a year ago, maybe 2 years ago now. So it's the goal here is to find some. Okay. The goal now is to find some spontaneous symmetry breaking of this time translational symmetry. It's kind of an analogy of this normal space crystal, which is a symmetry breaking of the space translational symmetry. So now we want to see whether this can happen in the time domain. So in the quantum region, basically you want to find a Hamiltonian which is time independent by itself. So the Hamiltonian has a translational symmetry because it's t independent. And you want to find some ground state which automatically has some time dynamics. It breaks the translational symmetry, which means it's t dependent. So it will automatically have some motion, although the Hamiltonian by itself has no time dependence. The first question is whether this is possible. And actually, it's pretty non-trivial. At the first glance, it sounds just to be impossible. Why it's impossible? Because there's a well-known theory in quantum mechanics. Quantum mechanics is called Ehrenfest theorem, which states for any eigenstate of a time-independent Hamiltonian, if you look at the evolution of any operators, like operator O here, if you look at these gradients, it's just zero. Why it's zero? It's just one line of mathematics. If you look at this this evolution from the Helmholtz equation is given by this commutator, right? And because this is the eigenstate of the Hamiltonian, you can easily apply this H apply on this psi E is just the energy. You can take this energy out because the energy commutes with everything. So you have something is O minus O, which is just zero. So that means if you look at the exact ground state, exact eigenstate, which of course includes ground state, there should be no time dynamics for any operator. Then one still, so with that, the question is whether one still bother with this. Of course, this sounds to be impossible now. So the first question we need to clarify here is actually we are not looking for exact ground state, because for that, there's no time dynamics. What we look for is some effect ground state. So what's the concept of this effect ground state? This concept is actually pretty common. It's for many many-body systems. So what's the effect ground state? The definition here, there are 2 points. First, for the effect ground state, the energy will be slightly higher than the exact ground state. So it's in that sense, it's not a true ground state, but the energy difference is pretty small, it's tiny. And normally we require the energy difference go to zero when the system size goes to infinity. So in terms of energy, there's a small penalty, but the penalty is kind of negligible. So in experiments, this you cannot resolve this energy difference. And then why we still select out this effect state? It has the energy penalty, but it's still non-zero. We are interested in the effect state because it's more robust. It's selected out because of its noise robustness. It's not because of its strictly no energy, but because of its more robust to noise. And there are actually many examples of this effect ground state, and many states of matter we see every day is actually effect ground state instead of a true exact ground state. And let's just give two simple examples. For the first example, we look at this familiar, this IC model. We have a ZZ interaction IC model with a transferred magnetic field. And we know for this model there's a well-known phase transition. When you change this B field from larger than 1 to smaller than 1, there's a transition from a polarized state to a ferromagnetic state. And now we look at the region in the ferromagnetic state. And normally we take the ferromagnetic state as something as a spin or pointing up or pointing down. That's our normal state. But this state is actually an effective state. It's not the exact state. Because if you can easily look at this Hamiltonian. As long as this B is non-zero, this B is still smaller than 1, it's still in the ferromagnetic region, but it's non-zero. In that case, you can easily see the exact ground state should be a big quantum stable position state. They should have all spin up plus all spin down. It's like a general cat state. But the energy difference between this simple ferromagnetic state and this general cat state quickly approaches 0 when the system size increases. So the energy difference is really small, it's really tiny. And on the other hand, this ferromagnetic state is much more stable. If you have some random noise, for real experimental system, there's always some random local noise. And that noise will tend to select out this ferromagnetic state. So that we always know that we also know this general cat state is very sensitive to noise. So in practice, we can easily see this state will weigh out. And that's an example of the effective state. And as a second example, we just look at the normal space crystal. The space crystal, the Hamiltonian for the whole system can be written in these forms. This is some interaction part, and this is for the central mass motion, And this is the kinetic energy terms. If you look at the exact ground state, this ground state should be a momentum eigenstate, right? Because this Hamiltonian is a kinetic energy. Its eigenstate should have a momentum 0. So the state should always be delocalized. But from our experience, normally we have a crystal is always localized in space. So this localized crystal state is again a effect ground state. The energy difference between this localized state and the delocalized state is 10 to 0, and the localized crystal is snagged out still by this robustness. It's more robust to local noise. So the local noise tend to localize this state. So that's an important point we need to clarify here, because there's a lot of controversy which is actually related to the difference between the effective state and the exact state. And here we need to keep in mind the space-time crystal or the time crystal here, everything is only an effect ground state. Okay, so how to realize this kind of state? We just give one example here. And for this example, we consider trapped ion systems in a ring trap. And you just apply some magnetic field, which is perpendicular to this ring trap. And then you can easily write down the Hamiltonian for these systems. The Hamiltonian has two parts. The last part is just kinetic, it's just some interaction with the ions have quantum interaction with each other. So this corresponds to the quantum interaction. It's basically 1 over R potential. This is basically R, the difference, the energy, the distance between the ions. And the phi here is correspond to the angle along this range. So this sine phi I, phi j means that it's basically the distance between these ions. So this is basically it's basically R I j. So that's a distance between the I and the j ions. So that's a quantum interaction part. And the first part corresponds to the kinetic energy for all these ions. And we have R here because that's from this magnetic field. We know if you apply magnetic field for the quantum mechanics, the kinetic energy should be replaced by this effective momentum operator. So that's the R part. R corresponds to the magnetic flux going through this ring, and the unit here is taken as a flux unit. And for this Hamiltonian, one thing to note here is for typical experimental parameters, this eta square characterizes the ratio between the interaction energy and the kinetic energy. And this ratio is actually huge for typical systems. It's about 10 to the 9th for typical ions. So the interaction energy is much higher than the kinetic energy, and we know in that region the ions will just form a Wegener crystal. We see this from all the experiments. So they should form a Wegener crystal. And then with the Wigner crystal, the ion will just have some small oscillation around the equilibrium position, right? So you expand that with the 4 modes. This is just very familiar with the trapped ion community. So you have this 4 modes, and the kinetic, this part, the kinetic energy corresponds to the central mass motion. You have a ring, you have the ions oscillate around the 4 modes, but you still, the whole ring can still rotate. That's the central mass motion. So this P corresponds to the central mass momentum here, and alpha now, because it's this n ions together, you have n alpha. You know, the relative motion is just captured by these 4 modes. This corresponds to the relative motion between the ions. This corresponds to the central mass motion. So it has these 2 parts. So that's a Hamiltonian for the whole system. It's certainly time independent. So now we want to see how what's the ground state, what's the state of the Hamiltonian, how to minimize the energy for the whole system. Okay, now if you look at this Hamiltonian, we try to find the energy spectrum for this whole system here. And if you look at this spectrum, the last part is actually just the interaction part. And to minimize the energy, you just want to take Ni equal to 0, right? Because the energy gap is eta h bar omega, which is kind of huge, which is very large. So you just take all Ni equal to 0. So that's a ground state. And then we should look at the first term. The first term here, this corresponds to the rotation in this ring. And in that ring, you need to satisfy the periodic boundary condition, right? So the wave function for the central mass can be written in these forms, where this k should be an integer. The k is a momentum, should be an integer to satisfy this boundary condition. So that will give you this kind of energy spectrums, where this k is an integer here. And that's just a first step. But actually, we have a more constraint on that. If this is true, then the energy difference between different k is very small. It's proportional to 1 over n, right? This m is because this n is the total mass of the central mass motion for the central mass degrees of freedom. So if this is true, the energy difference will be really tiny, and that will be pretty bad. But actually, there's an interesting identical particle effect for these systems. Even this system, even the ions is localized, the identical particle effects still make a difference. Why is that? Because apart from this periodic boundary condition, the ions need to satisfy some additional constraint. This is the ion rings. If you just rotate these rings, if you move ions from this side to this side, for instance, because all these ions are identical, when you just move from here to here, then the whole system shouldn't change, right? Because it's identical particles. This just corresponds to an exchange of 1 ions with all the other m-1 ions by 1 step. And because of the identical particle, we require this wave function shouldn't change for bosons. For bosons, if you just rotate this seat by 2 pi over n, which corresponds to move this ion from to this position. So for bosons, there should be no change. For fermions, you will capture a phase factor. And what's the phase factor? It depends on how many ions in the systems. It's basically m-1 because it's a change of 1 ions with all the other m-1 ions. So there's a non-trivial identical particle effect which puts an additional constraint on this wave function. And because of this additional constraint, this k here cannot be an arbitrary integer, but instead this k needs to satisfy this condition. It needs to be times n times k prime, where this k prime should be an integer for these boson systems or for odd number of fermions, which means that there should be no phase change, no sign change. For even number of fermions, there's 1 sign change, so this k prime should be a half integer instead of an integer. So the whole spectrum should be written in these forms, where k is n times k primes, and this n cancel with this n. So now the energy difference will be proportional to n instead of proportional to 1 over n, which makes the energy gap significantly larger. It's significantly larger if you have a larger n. So that's actually a good system to realize. It's a good property to realize this. You want to realize a ground state, and you want to have other states which is higher by a significant energy gap. Otherwise, it's very hard to realize that. So that's a good property from identical particles. And with this effect, then now we try to look at the ground state. What's the ground state? The ground state for this central mass motion. So if this alpha is 0, then the ground state is simple. You just take K prime equals 0. Then it's it's a crystal at rest. But if this alpha is non-zero, then to minimize this energy, this K prime should be some integer which is closest to this alpha, right? And when this K prime is non-zero, this means the whole system should rotate. So you will automatically have some motion of the whole systems. Even the Hamiltonian is time independent, the whole crystal will have a non-zero momentum, and that means the ground state will rotate. So that's a way how to realize this ground state motion here. So this just shows what's the momentum difference, the momentum dependence on this different alpha here. This alpha, remember, this alpha is a flux going through this ray. And when alpha, this is for bosonic systems. When alpha is 0, the momentum is 0, and when alpha is 1/2, the momentum attains the maximum. You take K equal to 1, so the whole system will automatically rotate. And that's for bosons. And for fermions, it's a bit different because of this sign difference. Instead, for when alpha equals 0, there's some maximum motion already. So this is again due to the statistics. For the even number of fermions, they cannot stay in the 0 state because of the Pauli exclusion principle. So one of the ions need to rotate, so the whole center of mass motion need to rotate. So that's a way to get this ground state motion. And to realize the whole system, you need to have a very low temperature. Again, the energy gap will make a difference here. The whole temperature needs to be smaller than the energy gap. Otherwise, you have some left rotating state and some right rotating state. They will cancel with each other. And this just shows how the momentum depends on this temperature. Actually, the Jason did the detailed calculation for all this, and he's also in the audience, so you can talk with him for more details. So basically, for different alpha, for different alpha, there's a transition temperature here. When the temperature is larger than the transition temperature T star, then the momentum is almost 0, which just means the left side motion and the right side motion cancel with each other. So, sorry, what is T star? T star is basically a temperature scale here, and for this system, the T star is basically similar to a transition temperature. When T star is above the scale of the energy gap. So when when the temperature is above the energy gap, then you get some excited state. Something are left rotating, something are right rotating. They cancel with each other. So you need your temperature to be significantly less than the energy gap, and this T star is above the energy scale of the energy gap. So that's why you have this phenomenon. When you only have this rotation when T is smaller than this T star. And what's the scale of this T star? Actually, is still a very challenging experiment because the T star is very small. And the T star, of course, for T star scales with this energy unit before. So it goes down with this radius of this trap. This d is basically the radius of this ring trap. And it also increase when the mass of the ions gets smaller. So one can actually see this from this energy unit here. You can see all the energy unit is given by 1/mr². This r is basically the radius of the trap, and m is the mass. So with a smaller mass and with a smaller radius, you will have a bigger energy scale. You have a bigger energy gap. So this figure basically shows that kind of scaling. So the T star scales down with d by 1/r², and scales with it's scaled with m by 1/m here. So for instance, the barium ions will be better than the magnesium ions in terms of the energy, in terms of this T star, and the electron will be even better, but we don't know how to trap electrons. So that's a kind of energy scale for bariums. If you take this trap about 10 micron or 100 micron, then the T star is actually very small. It's less than microkelvin. It's between nanokelvin to microkelvin. So that's kind of a challenging thing for the experimental realization. But in principle, we can show for these systems, if you have a of a mesoscopic systems, maybe with tens of ions to hundreds of ions, and it's trapped in a rain trap. And if you just cool the whole system down, at the high temperature, you have no rotation. If you just cool down the systems, and at the low temperature, you should have some automatic rotation. And that's basically a realization of the time crystal at some mesoscopic scale. And this is just the last slide for this topic. It's basically a realization of this rain trap, as we knew. There's some rain quadrupole trap realized already with the experimental systems. Or you can consider a linear octuple trap. For a linear octuple trap, the minimum of the potential minimum also forms a rings. So this is a way to realize some small rings. If you want to realize some small rings, maybe this is easier compared with the other ring traps. So that's a kind of a brief explanation of this idea of the space-time crystal and its realization with the trapped ion systems. Yeah. Actually, sorry, I don't go to too much detail. If this is the whole thing rotation, this rotation is actually an exact ground state. But the rotation doesn't automatically break the symmetry yet, breaks the time translational symmetry yet. Because what's that? Because the whole system is a momentum eigenstate. So the momentum eigenstate means the wave function is delocalized, right? If you look at the center of mass motion, the whole wave function is delocalized. And if you want to really break this symmetry, the wave function needs to be somewhat localized. You need to have a kind of motion. You have wave packet move around. If you look at this wave packet, then you need to have a small pinning potential. You need to add a small pinning potential to this rain trap, and that will localize. That's like a noise. This noise will localize your wave packet, and then the wave packet will rotate. But if you have a wave packet which is rotating, then the energy of this wave packet will be slightly higher than this momentum eigenstate. And that energy difference basically goes to 0 when n is bigger, or it's basically scaled with 1 over n, something like that. So that's why if you really want to have a symmetry breaking state, it's only an effective state. But if you just want to observe a floating crystal, this motion here, this momentum eigenstate, the non-zero momentum motion, that's an exact ground state.
Can I add to that? But because it depends on the quantum statistics of the atom,
yeah,
each atom is somewhat localized, but also it must overlap. Its wave function must overlap all the others.
Yeah, if you look at the center of mass motion, yes, because the center of mass is unlocalized. So if you look at the relative motion, the relative difference between this atom and this atom is well defined. But I cannot define what's the exact position of this atom because the center of mass motion is delocalized. So in that sense, it's still the whole system is still delocalized.
But it's not flat. It's not flat all the way around. It has spatial wave function has a bunch of humps, but you don't know which atom goes with which hump.
If you look at center of mass motion, it's actually flat. But because the center of mass is like you average over the whole systems, then it's still flat. Yeah. If you look at the correlation between this position and this position, the correlation should have a crystal order, right? Yeah.
You increase the number of ions, is then the speed slower, or because
if you increase the number of ions?
Yeah.
If you increase the number of ions, the speed is the momentum is the same, right? Yeah, the momentum is the same.
But it's now more particles, no? So are you talking about the whole system?
The K will be the same. I think if you look at this phenomenon, look at this formula, the K is independent of the number of ions. So when you increase the number of ions, the momentum, the K will be still the same. The velocity actually goes down, right? Because the K is a momentum. When you have more, I think the velocity probably goes down, but the K is the same. Because the total mass increase with the number of ions. Yeah. Yeah, but the momentum is the same. Yeah.
So in connection with the question of crystal, so you start from a crystalline state.
Yeah.
So this is going to be a classical ground state.
Yeah.
So all the particles are distinguishable, and this is the starting point for looking at the vibrations around the equilibrium positions.
This equilibrium position, we just have a floating equilibrium position. So it's the equilibrium position is not usually probably we can say that if you look at the distance between these different ions, the distance is kind of well fixed. So you can basically expand your distance around that, and that gives you the relative motion. Because center of mass motion is basically rotating around. So when you get the final modes, I think you can do an expansion around the average distance. Maybe this is a more appropriate language. So because there's no well-defined equilibrium position for each ion because they are rotating, but there's a well-defined distance between the neighboring ions, and you can do an expansion around this average or equilibrium distance. Yeah.
I can't vouch for this, but you have some critics out there. Right?
Okay.
This fellow. Gruber, he had this recent paper which makes some really strong statements against this idea. So what is your take on that?
Yeah, it's the basic point here is for these systems we cannot take the. There's some other point like one confusion is about the effect ground state and the exact ground state, but I think that should be pretty clear. We look for effect ground state. But the major criticism on this is we cannot take the infinite limit. It's because this n should be finite. Why is that? Because you consider a range of a finite range, and finite range with a finite range you cannot put an infinite number of particles there. So you cannot take the thermodynamic limit, which means for these systems there is no thermodynamic limit, because when the thermodynamic limit, the density will go to infinity. That's basically the point of the criticism. But I think for experimental realization, that's not a problem because you need to work with a finite system anyway. As long as this n is big enough, there's no essential difference between an infinite systems and a big system because every experiment is a finite systems. But I think his point is more on a conceptual point. It's whether you can take an infinite limit, whether you can take a thermodynamic limit. And indeed, for this realization, we cannot take the thermodynamic limit. You cannot let n tend to infinity because in that limit, the density just goes to infinity.
That's assuming a constant radius.
That's assuming the constant radius. So the problem there is if you want to fix the density, and if you want to increase n, then the radius will increase, right? And when the radius is increased, you can see here this energy scale will become smaller. And this goes at 1 over r squared. So if you really fix the density and take infinite systems, then the energy difference just goes to 0. The energy gap, because this goes at this n, there's the n here, but this scales with n times r over r squared, right? When you fix the density, this n over r squared will go to 0. So if you just fix the density and go to infinite systems, the energy gap disappears. And that means the transition temperature goes to 0. So that's why you cannot take a thermodynamic limit for these systems. But you can work with the finite systems, and you can still get this phenomenon. So this is more kind of a realization of the time crystal at a macroscopic scale. It's not an infinite scale, where the energy difference goes to 0, but now you can, finite system should be okay. Yeah, I don't know, is that explain the point? Yeah.
Well, I can talk to you later.
Okay, yeah.
So what determines alpha?
Alpha is just flux. The M is a magnetic field times area of this ring.
So there's actually a magnetic field going through the ring?
Yeah, it's a magnetic field. It's a flux. It's a magnetic field times the area of this ring and divided by some unit, by some flux unit. Yeah.
But is it true that the energy scale you need to get to is independent of the magnetic field that you apply?
Yes.
So whether it's 1 Gauss or a kilogauss?
There should be a periodic. It's a periodic, so because with this alpha, it's a periodic system. So you need to only apply a pretty small magnetic field. If you increase the magnetic field, it's just periodic. The key it's given by this kind of shape. It's a periodic shape.
Actually, are you done with the talk?
Oh, no. Oh, sorry.
No, it's fine to have. We have plenty of time for the inline discussions, but
okay.
feel free to take charge.
Okay. I still have another half. Okay. Probably this part is shorter. So, okay. So, this is a kind of unrelated, but it's related with this is also done in collaboration with Jason. So you can still talk with him for more details. And for this topic, we want to look at some transition, some dynamic phase transitions. First, I want to clarify the concept here again. Actually, this concept is a little bit confusing. There at least it has two meanings, two kind of independent meanings. The first meaning is one could have a transition of dynamic phases. What that means is you change some parameter of your Hamiltonian or of your Maxwell equation, then the dynamics of the whole system will have some dramatic change. And an example of that is some like these damped harmonic oscillators. If you change the damping rate, there will be a sharp transition from a damped region to some damped oscillations to some overdamped region. That's a kind of an example of transition of the dynamic phase. There's another different meaning of this dynamic phase transition. It's basically like a dynamic transition of different phases. What that means is that during the dynamics of the whole systems, there are two different kind of time scales emerges. And an example for that is just pre-thermalization phenomenon. So before the system eventually thermalizes, we consider an isolated system, it can still be thermalized. That's kind of a hot topic recently. But before that, you can have some pre-thermalization phenomenon. It's a kind of like a metastable state, which will be stable for a long time, and in practice, it's just like a forever. And in the classical region, this is like a glass state. All the glass states. Glass state is not really the ground state. It all really is a thermal state. It's kind of a metastable state. But for practical purpose, it's basically stable forever. And pre-thermalization is something similar to that, but we consider that in a quantum system, in a really isolated quantum system, we still can see some of this kind of unusual phenomenon. So what's the example to see that? We take a pretty simple example, which actually has been already realized with by experiments. For instance, with the Chris group, we have this kind of Hamiltonians. This is a well-known IC model. You have X interaction, but with a long range, and this is very nice just with two laser beams, two laser kicks. You can have this kind of effect with XX coupling. And you can also apply effective transverse magnetic field. This is also from the laser beams. You change the relative phase difference between the lasers. You can get this effective Y terms. So, and this J idea is just coupling rate. It's a long range. It's given by it has a contribution of all these Fano modes. And this mu is just detuning. And this is just a mode function for the different Fano modes. This eigenfrequency there. So that's a kind of something realized already with the experiments. So now we want to use this kind of experimentally realized Hamiltonian to study some non-trivial dynamic transition behaviors. So we still take this Hamiltonian, but look at it in a particular region where this omega b, the transfer field, is much larger than the Gij, than the coupling rate. And it's pretty easy to realize that region. You just tune the relative phase between the lasers. You can get that region. And in that region, what you get is actually effective. Is instead of this IC model, you get effective XY model. Why is that? Because you can define everything in this sigma y eigenbasis. This term dominates. So you just define your spin up, spin down as eigenstates of this sigma y Hamiltonian. So now my up down is not an eigenstate of sigma z, but instead it's an eigenstate of sigma y Hamiltonian. And in this sigma y eigenbasis, then the Tudor spin should be conserved because you can have a spin flip-flop process. But if you expand this sigma x, you have some process with two spins both pointing up. You have a sigma plus, sigma I plus, sigma j plus. And that term should be forbidden by this energy cost. Because if you create two spin up atoms from two spin down, it will have a significant energy cost given by omega b. And when this omega b is much larger than this coupling rate j, this process should be forbidden. So that's so that term is basically removed by this term. So then you just get a sigma plus, sigma minus, and that's an XY Hamiltonian. So that's a way to get an XY effective XY interaction starting from this ZZ Hamiltonian, XX Hamiltonian. So with this XY model with a transfer magnetic field, now you just want to study its dynamics. And for these systems, the Hilbert space is divided into a number of different subspaces. And each subspace is characterized by a conservation of the total spins, right? Again, these total spins defining the sigma y basis. So the total number of spins pointing up minus the total spin pointing down should be conserved. So we just look at a particular Hilbert space, look at a simple example. You just have one spin up and all the spin down. And that's a very simple Hilbert space. The dimension of this Hilbert space only scales linearly with the number of ions. So it's pretty easy to do calculation in that subspace. And in that subspace, we take a particular initial state, just one spin up at the edge, and all the other spin down. And you can prepare this state, of course, from by a localized laser beams. You should be able to prepare this state. So we just look at the evolution of the whole systems, starting with this initial state and with this Hamiltonian. How the spin dynamics, what's the spin dynamics, how the spins evolves under this Hamiltonian under state. And this evolution sounds to be pretty simple, but it actually shows pretty rich and interesting behavior already. And the first thing we note that is that we have a long range interaction here, and you can tune the effective interaction range by this laser detuning here. When the laser detuning is close to the center of mass mode, we know it's almost have a constant interaction. And when the laser detuning is far away from that, we have a 1/r cube interaction. That's a dipole-dipole interaction. And if you get something between, basically you can get something like a 1/r alpha interaction here. It's like a polynomial interaction, and these polynomial parameters can be tuned over a wide range. And this has been, of course, realized already with this recent experiment from Chris' group. So we can take this detuning mu as an effective parameter, and we feed this alpha. So now in our later calculation, we just use this alpha as a feeding parameter to denote the different behaviors. And to show the dynamics, we define one effective order parameter. This order parameter is basically the position of these spin-down atoms. So the position of spin-down atoms at the beginning is at the left side, and we normalize that, and we call that position as 0. And then when it moves to the right side, we call that position 1. So it's something to change between 0 and 1. Then when you look at the dynamics, this is from some numeric calculation. And at the beginning, you should at the left side, so it starts with 0. And it's this is for the short range interaction. When this alpha is about 2.4, it's an effectively short range interaction. You can see the behavior is like an oscillation. It goes back and forth. The spin down atom first move to this spin up first move to the right side and move back. It has some oscillation patterns. That's a short range dynamics. But you can see this different behavior already when you move to the long range interaction. For instance, when you take this alpha equal to 0.6, that corresponds to a long range interaction. And the movement here is quite different already. First, you have see it's not an oscillation, but instead it's a kind of a random motion. And they cannot cross this 0.5. You probably cannot see this label. This is 0.5 instead of 1. So now these spin up atoms cannot move to the right side, and they can only move to less than half of this chain, and they will be reflected back. So that's like something there's like a boundary here. The ions, the spin up only move to the left half, and then will be bounced back. So you see many bounce from this 0.5 here. So even in the short range dynamics, you have seen some different behavior already. And the difference is more dramatic when you look at the long range dynamics, if you look at the long time evolution. And to look at this long time evolution, we still take this spin down position, but we do some average over the short time dynamics. So the short time dynamics is average out. You can see the long time behavior. And this is again for the short range interaction. It will quickly approach a thermal state where the position is at 0.5. So basically the average position of the chain is 0.5. So and that state has a symmetry, has a left-right symmetry, right? And if you look at the case with the long range interaction with again this alpha equal to 0.6, you can see 2 time scales appears. First, the system approach to something which is still on the left side is less than 0.5 and stay there for a quite long time. This is a logarithmic scale. So this time is actually for experiments. you can only see this time scale. This time is it's very long already. If you let the time tend to infinity, it still approach to a thermal state with 0.5. But for experiments, normally you can only see this region. And for that region, you cannot see a thermal state, but instead it's a plateau here that corresponds to a pre-thermal state. It's some better stable state, which will be stable there for a long time before the system eventually approaches a thermal state. And in this pre-thermal state, it actually breaks this left-right symmetry. The thermal state has a left-right symmetry, and but for the pre-thermal state, it still has some memory of the initial state. So it breaks this left-right symmetry there. And this just changes how the system behavior varies when you change this parameter alpha here. When this alpha is less than -1, which corresponds to a short range in direction, and you just the system directly approaches the thermal state. That's something here. It approaches to 0.5. When alpha is less than 0.1, you will have a pre-thermal state. This just means that there's some pre-thermal state in the middle region. And when alpha is 0, that's a particular region. When alpha is 0, the system is an integrable system. In the integral limit, one can show that this position, the average position of this spin up, is given by 1/n. That's an analytical result. And when n tends to infinity, which means this spin up cannot move, they basically stabilize at the left side. So you can see there are 3 different behaviors. When you change alpha, there's some sharp change of this dynamic behavior. So this is more like a transition of this dynamic phase. So we can see from this example, we have two types of transitions. You can see both the pre-thermalization behavior, which is like a dynamic transition of different phases, and you can also see the transition of dynamic phases when you change the parameter alpha here. You have different parameter, you have different dynamic behaviors. So that's basically my last slide, and the last is just a summary. So that's kind of my talk. Thank you for your attention.
Time for a few questions. Continue our discussion before.
Yes.
Yes. Is there a way of intuitively understanding why there's a plateau?
Why there's a plateau? The reason for that, the basic physical reason for that is there are 2 different time scales emerged from the systems. So there are some spectral properties of the eigenspectrums of this Hamiltonian. And there are 2 widely different time scales. Or you can say there are 2 widely different energy scales. There's one energy scale, which is a normal energy scale. It's pretty big, and that will lead to the thermalization, pre-thermalization behavior. And there's a very tiny time scale, or very tiny energy scale. And that time scale corresponds to the time scale for the eventual thermalization. So why we have that? Because there are 2 different time scales appears in the Hamiltonian. But why there are 2 different time scales, we don't know why. But basically it happens.
Yep.
What I similarly related to this pre-thermalization.
Yeah.
If I waited long enough,
yeah,
when I was in this region between 0 and 1,
yeah,
is it going to cross that boundary? I mean, is it just that it's has to attempt it so many times before eventually it'll be able to get across, or it doesn't never cross?
You mean cross which one?
From one half to the other half, you said.
Yeah, eventually it will cross. So eventually it will cross. So mostly it bounce back and forth many times in the left region, and eventually it will cross, and that will eventually go to the thermalization region.
And it'll be stuck on that side for some time.
Yeah. So it stalks with the left side for a long times. That corresponds to the pre-thermalization behavior, and eventually it will cross and eventually thermalize.
Now, are there? I guess for the number. So how many ions have you?
Similar to a few hundred ions. It's the largest one is 256.
Now, are there any in this plot? Are there any possibilities of the system being integrable? Or
integrable is
it's only that one case where it's
the alpha equals 0 case is an integrable system, and for the other case, it's not an integrable system. I don't think it's an integrable system.
Not general, but
it's still calculation is still tractable. It's because the Hilbert space dimension only goes linearly for this particular initial state.
I'm just wondering if you only have 60 or 100 ions, if you could tune something to to be very close to a solution that happens to be integrable? Is there any way to, or do you want to just say that there's no way to find a solution other than alpha equals 0 where the thing is integrable?
Yeah, I think for analytic solution, I don't know is there any. I don't think there's an analytic solution except alpha equals 0 case.
So let's say if you could tune the coupling, you may not have just the power law, but specific values. Then you can have this kind of perfect state transfer where
it could be weird
spin just would perfectly go to the other end and back, but then you have to engineer the coupling specifically. So,
yeah, so maybe that's not a realistic thing, or maybe it's super sensitive.
I think there's a number of subtleties here. First, if you just have this 1 over alpha, just have this 1 over alpha interaction. Yeah. In that case, you actually don't have this pre-harmonization behavior. We really take the real physical systems where you have you tune this mu. Okay. And it's close to 1 over alpha interaction, but it's not exactly. And that small difference make a difference.
So the inhomogeneity is important.
Yeah, yeah.
Oh.
And if you really have exact 1 over alpha interaction, you don't see this phenomenon.
So does this new energy scale then come from the fluctuations about that power law? Is that what gives rise to it?
I don't know the exact reason why it appears there are 2 time scale, but basically our numerical calculation shows when we are puzzled by this phenomenon, the numerical calculation shows there are 2 different time scales there, and the time scale only appears when you have this real inhomogeneous trap like the experimental case.
So you say the inhomogeneity of the system really needs to be there?
Actually, I cannot claim that, but what I can claim is that if you have exactly 1 over alpha interaction, you will not see this phenomenon. And if I take the real experimental case, I see this phenomenon. Whether this inhomogeneity is critical, I don't know. But it's, at least for this example, this is important.
So, I mean, basically what this triggered in my mind is maybe you can see this as like an impedance mismatch problem. So you have a wave or some excitation tries to go to the center, but the impedance or whatever changes and the wave gets reflected.
Yeah.
So, I mean, it seems like there are 2 kinds of inhomogeneities. One is that in space, I minus j is not really distance. Because in a harmonic trapped chain, but there's also inhomogeneities in the couplings themselves between I and j. I wonder which one is important. Maybe they're both important. Maybe it doesn't matter.
Yeah, I think the real physical reason is one should appear there should 2 different time scales emerged from your Hamiltonian. But which Hamiltonian will have this kind of widely different time energy scales? I don't know. I just don't have an intuitive picture for that. But at least for this example, it appears.
Well, with that, we better conclude because it's lunchtime. And before we get noisy and so forth, I was saying there are lots of eateries in Harvard Square, and even to the north, there's a few squares, right? In that direction. Okay. So have a fun lunch, and we will convene at 2 o'clock right here.